This week in lab on your syllabus, it's another week where you have 2 experiments listed on your syllabus. The doing in lab, for the most part, is experiment 12, so the reaction you're going to run, and the doing in lab and what you should pre-lab is experiment 12. Experiment 13 will teach you about thin layer chromatography. So there's some diagrams and so forth that you should take out of experiment 13, but for the most part, your pre-lab should be about experiment 12. You'll have a quiz this week as always, and there's nothing to do this week. So the week off before the long haul to the end of the semester. Next week, so we don't have lab on Thursday. Obviously, you all will be somewhere else besides sitting in the Science Center or in here because it's Thanksgiving. So there's no pre-lab lecture next Monday. All right. However, your experiment 8 and 11 report is due, so find out from your lab prof when, how you are turning that in, and make sure you get your GC data from your lab prof. All of the GC data, all the samples that were submitted, all that data has been collected, and it's distributed back to the prof. So make sure you get that GC data this week from your lab prof, as well as the standards that pertain to your particular lab section. Okay? So we're now approaching this time. Final exam, so I'll keep reminding you of this, but the final exam, all of us gathering together at once, is December 14th, so the Monday of exam week, in here from 12:30 to 2:30. So we're in the middle of the day exam, okay? And we will all be getting together all at once to take that exam, all lab sections all together. So that is the time, the exam time for this lecture, Monday, Wednesday, Friday, 4 o'clock lectures. Okay, bunch of changes with Open Lab, so I've put them up here. Wednesday, Open Lab, 9:30 to 3:30 as usual, okay? Friday, most of the chem faculty will not be available later in the afternoon. So what we are doing Friday is we will open the labs at 8:30 in the morning. Dr. Johnson is going to open them for everyone as soon as he gets here. But we will be closing them, sorry, not at 12, or not at 1, at 12 p.m. on Friday. So this Friday of this week, labs will close at 12 o'clock. Next week, Monday, regular open lab time, so a week from today. Tuesday, because we don't have designated lab next week, we will have the labs open for Open Lab on Tuesday. All right, so from 8:30 a.m. to 4 p.m., the labs will be open for Open Lab. So you'll have another day of Open Lab next Tuesday. Wednesday, we'll have them open from 9:30 a.m. to 12 p.m. Usually by 12 p.m., everyone's decided they have better things to do than be in Open Lab, other more fun, exciting places to be. So just keep in mind all of these guys, and I'll leave this up here the entire time I'm talking so you guys can get all those times written down. All right, couple notes about experiment 8 and 11 before we talk about experiment 12 and 13. So with your GC data, you're going to need those standards that your lab prof is going to give you, and now you've got to take your data and look at the standards and put everything together, okay? Make sure you do use those standards, all right? Also think about what should have happened in experiment 8 and experiment 11 for what you were assigned to do. Whatever your reaction scheme was, you know, your alkyl bromide, your aldehyde, what final alcohol you were making, and then what was going to be the dehydration products from that alcohol. You need to think about what makes sense for that GC data, okay? So don't propose things because retention times match to correspond to things that don't make sense for what you have actually done, all right? So you've got to put the pieces together. We've got some standards, not all the standards, but you also have to think about your own reaction, what makes sense for your reaction, what should be there, what shouldn't be there. Be careful labeling anything an impurity. If you cannot figure out what a certain peak corresponds to in the end, using the standards, you should label it as an impurity, but be careful doing that. Make sure it's not something that is actually one of your products that you need to figure out from the standards and what you should have done in your experiment, okay? And then just make sure that you're looking at it and it makes reasonable sense for what you have done. Remember, things like if you have a trans product, you should probably have the cis product too. You know, cis and trans don't show up just trans, no cis, or just cis, no trans. Things like that should make sense in the data that you have. Okay, so be careful with that analysis because it's a big puzzle and everybody did different things and you've got to look specifically at your data and the standards to figure out what makes sense for your set of data. All right. The other thing to think about is if you see something in 8, do you see it again in 11? Think about, like, for example, the ketone that can have a retention time right before the alcohols. Those alcohols can oxidize to ketones and they have slightly shorter retention times. You didn't do anything in experiment 11 to get rid of ketone. So if you had ketone in experiment 8, you should still have ketone in experiment 11, okay? Now you shouldn't have a lot of alcohol left in experiment 11 after you've done the dehydration reaction. Same going back the other direction. You hopefully don't have a lot of alkene in experiment 8. You should have hopefully waited until experiment 11 to form a lot of that, okay? But look individually at 8 and 11, but also look at them together because you took one experiment's product and used it in the next experiment and the information is tied together and the impurities are tied together, okay? Same with the IR spectra. You should see a transformation between 8 and 11 in what you collected with the IR spectra, okay? And you should collect literature IR spectra for your alcohol and alkenes as well as your own experimental spectra. Just make sure it makes sense. So like 3-heptanol is your alcohol. If you can't find 3-heptanol, you found 4-heptanol. That would make sense for that IR spectrum, but don't use like 1-heptanol because that's more different than the same as 3-heptanol, okay? Same with the alkenes, you have a mixture of alkenes, so try and find one of your predominant alkenes, but you don't have to find all the possible alkenes for your literature spectrum, all right? And then be careful in looking for them. You want a liquid or neat sample. You do not want a vapor phase IR spectrum because that will look different than what you collected in lab, all right? So those are a couple cautionary notes for experiment 8 and 11. So now this week, experiment 12, we're going to be looking at a really important reaction, just like the Grignard reaction is, in organic chemistry. It's used quite often in lots of different arenas, in research labs, in industry, in all sorts of places. The Diels-Alder reaction is used, and it's named after Diels and Alder, so 2 people came across this reaction. They also got the Nobel Prize for it because that's how important a reaction it is. And so just be careful when you go to write about Diels and Alder. D and A need to be capitalized. So hint there for the reports. Now with this reaction, it's a really fun, neat reaction if you set it up just right because it goes really well, okay? And so there's certain pieces that are involved in the reaction. We've got a diene, so we'll talk about what's involved there. We've got a dienophile, so our diene is our piece that has two enes, right? So 2 double bonds. And then we have our dienophile, what wants the electrons from the diene. And they come together all in one step. So it's a concerted mechanism, all in one step. And we make a cyclic structure out of it, okay? So we make a ring out of it, so it's a very useful reaction. So it's considered concerted. We can also talk about it being pericyclic, so I'm going to put some of these things on the board as ways we describe the Diels-Alder reaction. It's a concerted mechanism, so one step. It's a pericyclic mechanism. So that means that we've got a single step with a cyclic transition state. So not an intermediate. We don't go through an intermediate. It's just a transition state. Cyclic talk about this as a 4 plus 2 mechanism. So we're talking about what's going on with our diene. 1, 2, 3, 4. 4 plus 2 pericyclic mechanism. Okay? So 4 carbons here, 2 carbons here that come together. What is involved, and you in lecture will talk more about how you set this up, but what you have is you've got your dienophile, or sorry, your diene, and the p orbitals involved in the double bonds, those sigma orbitals involved with the double bonds, and the overlap that you get between these orbitals of the diene as well as the orbitals of the dienophile, so that you can get electron flow. Basically, we've got electrons from 5, 6 from our dienophile donated to carbon 1, electrons between carbon 1 and 2 kick over, electrons between carbon 3 and 4 kick over to carbon 5, and then we form our 6-membered ring here from it. And it all has to do with this overlap. So in lecture, you're going to go through more detail of what needs to be involved here in setting up the overlap of those orbitals. But what also is important with this is the stereochemistry. You get one stereoisomer. We'll talk about that here in a minute, what is involved there. So if you can set up this reaction just right so it takes place really efficiently and well, you've got a lot of good things going for you. You've got carbon-carbon bond formation, making a ring. You've got certain stereochemistry that you're going to get out of the product. So it's a very predictable, nice reaction for getting certain compounds to work. So here's an example here, down here, of 1,3-butadiene, and then we're reacting with the melanate. And so the stereochemistry, we get only the endo and exo products of this possible ring formation. We only get the endo products. So I'll talk about that here in a minute, what is involved with that. So what we've got with these orbitals that need to overlap, there's 2 ways they can come together. So they can come together so they're kind of barely overlapping, or we can have them come together where they basically sit on top of each other. And what we want for this reaction to work is we want maximum orbital overlap. And so what happens when you get that maximum overlap, so the left-hand side is showing that maximum overlap versus the right-hand side, we get what is called the endo product, okay? And when we talk about the endo product, we're talking in reference to this bridge here, the largest carbon bridge, so not our 1-carbon bridge, but our 2-carbon bridge here. So the endo product is more our kind of going down product versus our exo product off of the carbons here would be more going out. And so it all comes from setting up this orbital overlap, okay? So big thing with the stereochemistry is that we get the endo product is what is formed. So now a couple things we need to talk about before we look at our specific reaction is the pieces. So we've got our diene and we've got our dienophile. And what is needed to make this reaction work well with both of these? Okay, so the diene, it wants to have a certain conformation for the best overlap. And what it is called, this is the S-cis conformation is what you want for the diene, okay? So you want it so that it's got its orbitals and its carbons all going in the same direction so it can have maximum overlap versus If we've got something here that's got to rotate back and forth, we're not going to get a good reaction. So what we don't want is this, right? Okay? So we want the S-cis conformation versus having the trans conformation. With the dienophile, what it wants is it wants to be able to react with this electron-rich diene. And so what would make it really happy is having some electron withdrawing groups on it to make it more reactive. So we could just use ethylene, okay, as our dienophile, but it's not super duper reactive towards the deal of wanting to react even with 1,3-butadiene. It would happen, but it'd be really slow. If we can make this more electron withdrawing and put electron withdrawing groups on it so it really wants some of that electron density, it's going to make it a lot more reactive. So what we could have is something like this, where we have an aldehyde attached to that ethylene, okay? Or we could have something like we make an ester attached. Now all of a sudden we've got electron withdrawing groups off of one of these carbons. Is making this much more reactive to something that has electron density, all right? So S-cis conformation for the diene, electron withdrawing groups are really important for the dienophile. Now the reaction that we're going to use, we've set it up so that we've got all the right pieces together, okay? So we are going to use cyclopentadiene. Well, because of the ring of cyclopentadiene, we definitely have that S-cis conformation. Okay, there's no question about that. We don't have to worry about it going back and forth. It is set. Our dienophile, N-phenolmalamide, is it has 2 electron withdrawing groups on it. Okay, so basically, even though the dienophile is part of this ring that's then attached to an aromatic ring, each of these carbonyls, or the imide, so the fact that we have basically 2 amides, so it's an imide, counts as 2 groups that are electron withdrawing to make it very reactive with the cyclopentadiene. Okay? And so we have the electron flow from our dienophile to carbon 1, kick around of the electrons and electrons back to carbon 5. So if we've got 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4 to 5, and it all started between 5 and 6. Then we get the Endo Product. And so this is the structure of the product for the reaction that you're going to be doing this week, okay? And this reaction works really nicely, really quickly. You're refluxing for 10 minutes. That's how good a reaction it is, okay? So it wants to go zippity-skippity because it's set up to react really well with each other. And basically all you've got in here are your 2 reactants, and you've got your ethyl acetate solvent. That's all you need to get the reaction to go, all right? Now, the one little caveat to this, which means that I get to come in super early for morning labs, is cyclopentadiene doesn't usually hang out as cyclopentadiene. It actually wants to hang out as its dimer. It likes to hang out as dicyclopentadiene, okay? And so what we have to do to get our cyclopentadiene is what's called a retro-Diels-Alder reaction. So 2 cyclopentadienes will react in a Diels-Alder reaction and go to dicyclopentadiene. What we buy is dicyclopentadiene, and so what we have to do is what's called cracking, where we will heat this up and then distill to get the cyclopentadiene as this form, not as the dimer, all right? And so this, being that it doesn't hang out very long, it has to be cracked right before you use it, and then we keep it really cold so it doesn't want to go back to dicyclopentadiene, okay? So right before lab this week, we'll be doing this. We'll be cracking it, and then you will get the cyclopentadiene from your lab prof because they'll be keeping it nice and cold for you until it's time for you to use it. All right. So you will dispense of the ethyl acetate solvent. You will dispense of the N-phenolmalleamide. Get this dissolved in the ethyl acetate. So you should have a solution, no solid hanging around. Then come see your lab prof. They'll give you your cyclopentadiene for your reaction. All right. And it really quickly will react. As soon as it goes in, it will start reacting. Even without stirring, even without refluxing, it'll react pretty quickly. Right? Okay, questions at all about the reaction? Okay, so let me just give you a couple things more for what is going to be going on as far as workup, and then the rest of the time we're going to talk about experiment 13, thin layer chromatography. So once you have the reaction complete, we're going to talk about how you're going to TLC the reaction here in a minute. But you're going to have your reaction is complete. You distill the ethyl acetate, abbreviation for ethyl acetate. Then you're going to precipitate it with hexane. Then you're going to recrystallize with ethanol, and then you add, follow your lab manual, you're going to add a little bit of water to help it crash out, okay? And then you'll get, so here you're going to have your crude product. So if anyone in TLC talks about needing to do something with your crude product, there it is. Now you're going to have your purified product. And you may be TLCing here, you definitely will be TLCing here. You're going to want yield, you're going to want melting point of the solid, and then you're going to want to collect the IR spectrum of that solid, all right? And so all of these steps are pretty straightforward, except for the new guy is going to be everything involved with TLC. Yes? We'll talk about that here in a second. So I just want you to note that you're going to have to do this, and then we'll talk about what's involved with that here in a second. Okay? As far as the IR, on Moodle, I will put the starting materials and product standard IR spectra up on Moodle. Okay, so your two starting materials are your cyclopentadiene and your N-phenolmalleamide. Your product then is your final product that I had up there just a second ago. That product IR will also be up there. All right. So all of this is things you've done before, pretty standard techniques, nothing new except for this guy. So now we're going to talk about that guy. Okay. So here is what is involved with TLC, and we'll talk about what TLC is here, and then what all we need to do. Okay, so TLC, very useful tool in organic chemistry, used all the time for monitoring reactions. It stands for thin layer chromatography. And unlike with GPC, we had our instrument working, or like last week with the GC, where you have to submit the sample to then be put on a big instrument and taken care of for you. Thin layer chromatography, you're going to take care of the doing with this guy yourself. Right? So it is chromatography. So what are the two pieces that we always have with chromatography? Mobile phase, right? Mobile phase, and then what's our other phase? And our stationary phase, and I'll talk about who those two are here in a second. The other thing with thin layer chromatography, and we'll talk about how this works. So with gel permeation chromatography, GPC, that was mainly a separation based on the size of the compound, how big that polymer was. GC, what was that mainly based off of? Volatility, boiling point of the compounds, right? Thin layer chromatography is a separation based on polarity of the compound. And so we'll talk about how that comes into play. But polarity is the big component to the separation with thin layer chromatography. Okay? So our mobile phase is our TLC solvent, which is also called the eluent. Our stationary phase is the silica. The silica itself, it's on polystyrene backing, okay, to make the plates, but it's the silica that is our stationary phase. So you'll see what these plates look like. They're cut as rectangular plates, and it's on the back is this polystyrene plastic backing. On top of it is the silica. So the white silica is what is important as far as the separation is concerned. And thin layer chromatography, like I said, is used many different fashions in organic chemistry. What you need is what's called a chromophore. And so you need to be able to see it either under UV light, or you have to use different types of stains to be able to see it. So you guys are fortunate that your N-phenolmalamide has a nice aromatic ring on it. Aromatic rings are very visible with UV light. So we're going to be able to use UV light to see what's going on with your TLC plate. Otherwise, if you didn't have a chromophore, you can use things called stains that can help you see what is on that TLC plate if you can't see it under a UV light. TLC is used for monitoring reactions, which is what we're going to use it for this week. You'll use it similarly next semester, but you can also use it for something you're also going to learn next semester, which is column chromatography, which is another separation technique. And column chromatography and thin layer chromatography basically are the same principles, using them in slightly different manner, but same idea pretty much. So we are going to be looking at the progress of our reaction with TLC. And so kind of the principles, basic principles involved. This is a drawing of a TLC plate. So you will have plates that have lines in pencil on the bottom. That's where you will be spotting from your reaction mixture, and then we'll be putting them in glass jars that will be used as our developing chamber. The way to prepare this chamber is you will have eluent, and the thing to be careful of with this is our eluent and our reaction solvent are very similar. So our eluent is 1:1 hexane to ethyl acetate. So 1 part hexane, 1 part ethyl acetate. It's a 1:1 mixture. Okay? That is what you use this week. Be careful, because there is this bottle in the reagent hood, and then there is also the bottle for the dry ethyl acetate that you need for your reaction. If you use this bottle instead of your ethyl acetate for your reaction, you won't get your dienophile to dissolve. So that's why I said make sure that you have it dissolved before you add the cyclopentadiene for it. Telltale of if you've got the right stuff, if it's ethyl acetate, it will dissolve. If it's not just ethyl acetate and it has something else in it or something completely different, it won't dissolve. So this is our eluent. This is what we use for TLC. Just the straight ethyl acetate you use for your reaction. You each will get a jar, and there's enough jars for every person to have 1 jar, so don't try and grab multiple jars because you have multiple TLC plates. What you're going to do is there's a jar with filter paper in it. You're going to put enough eluent in it so that it fills the bottom of the jar and comes up probably about half a centimeter or so. Fill it about a half centimeter up with eluent and then cap it. And what we want is that eluent to travel up that filter paper that's in there as well, because what we want is the atmosphere in that developing chamber to be completely in equilibrium of the solvent that's in there as well as the solvent vapor that is present, okay? So that's why we've got our filter paper in there. So before you develop your TLC plate, make sure that you prepare the developing chamber by putting the solvent in there and let it travel up the filter paper, then you're ready to use the developing chamber. Once we spot our TLC plate, then we'll set it in our developing chamber. When you put it in the developing chamber, you don't touch it. So once it's in the developing chamber, set it in your hood and don't put the cap on it carefully and don't move it around, okay? I'll show you in a minute what your TLC plates will look like if you move it around. You're going to let the solvent climb up until about 1 centimeter from the top of the plate, and then you're going to pull it out and under UV light look at what happened with your plate, okay? So the spotting of the TLC plates, so here is our generic TLC plate. You will get a plate with the silica on it, with the plastic backing that has the line drawn on the bottom, and then you are going to spot with capillaries on that line. So when you go to spot your TLC plates, you're spotting right on that line. So the capillaries, we also have to teach you how to make those, because you want them really, really thin so that these spots aren't really, really big. We want little spots, not big spots, okay? So this is our example of a TLC plate that has been prepared to be developed. And then after you get the TLC plate out, you still have the line that's on the bottom in pencil. In pencil, not pen, you will draw where that solvent line is. We still have where we spotted on the bottom, but now what should have happened is those spots have traveled up the silica in a certain way. So say we've got a spot here, and a spot here, and maybe another spot here, okay? So under the UV light, now you will see these spots and you will draw them in pencil. The reason you always use pencil with TLC plates is because ink pen has chromophores in it. It has lots of aromatic compounds in it, and so it will mess up what you see on the TLC plate if you use ink pen. You have to use pencil on TLC plates, okay? And you want to make sure, the other thing is pencil wants to etch the silica off, so you have to be careful. Don't use like the sharpest pencil. You kind of actually want it to be a little bit dull so you can circle things on it without etching away your silica. The other thing is your hands have lots of chromophores in them. So you have lots of aromatic compounds in your body. You don't want to put your fingerprints directly on the TLC plate, because then when you go to develop it, you'll see fingerprints on your TLC plate too, okay? So handle these guys from the sides, and then also make sure you wear gloves when you're handling the TLC plates so you don't get fingerprints all over them, okay? So this is the basics of just going from spotted TLC plate to a developed TLC plate, okay? So now let's talk about how this whole separation based on polarity works, all right? We've got this silica as our stationary phase is a really polar compound, okay? Our eluent is never going to be as polar or more polar than the silica. If we went to something that polar, this wouldn't work. We'd actually dissolve the silica, okay? So we're never going to have an eluent more polar than our silica. So as far as compounds go, things that are relatively non-polar will hang out more with the relatively non-polar eluent. Things that are more polar will hang out more with the more polar silica, okay? And so what you've got going on is this equilibrium of the compound, and it's going between eluent and the silica, the stationary phase, going back and forth. And depending on how polar this compound that you just spotted on the TLC plate is, it will either spend more time hanging out with the eluent or more time hanging out with the silica. But the spot itself is being adsorbed on the silica, and it's this equilibrium between the silica and the eluent that's helping it travel up the TLC plate. All right. So as the eluent's moving, you've got this whole equilibrium going on, back and forth, back and forth. Okay. It just depends on the polarity of the compound, whether the equilibrium's more this direction or the equilibrium's more this direction. Okay. So looking at this developed TLC plate, so let's put some letters here. Of the compounds that were developed, things that are more polar, that will hang out more with the silica, are going to travel less far up the TLC plate. So in this example, this would be the more polar compound. It hung out more with the silica instead of hanging out more with the eluent and traveling up the TLC plate. So these two compounds are less polar, and potentially the same compound, less polar than this compound. That good so far? Okay. So that's how the separation based on polarity works, separating the compounds out. Okay. Now we can tweak our system, which makes things a little bit more complicated. Okay. We can make our compounds move farther up the plate or less far up the plate depending on what we do with our eluent. Okay. So say we've got this plate here, and then we decided, you know what, we want everything to move farther up the plate when we develop it. So our goal is we want something like this instead of something like this. Okay? What you would do to go from here to here is make that eluent more polar. And so by doing that, this more polar compound wants to hang out in the eluent more, and these compounds that are already hanging out in the eluent are hanging out even more in the eluent and traveling higher up the plate. Okay? So if you want how far the spots travel to go higher up the plate, you want a more polar eluent. If you want them to travel less far, then you have a less polar eluent. So that's how you manipulate the polarity of the solvent. And so when we talk about what is going on with the spots with a TLC plate, what we use is what is called an RF factor. So the distance from the origin traveled by the compound divided by the distance from the origin traveled by the solvent gives a unique number, and that's how we talk about a particular compound on a TLC plate. All right? Now, does RF values have a unit? So if you're taking distance divided by distance, is there any unit on there? No. Okay? Are these numbers going to be greater than 1 or less than 1? Less than 1, right? Because you're taking this distance, so the origin to the spot divided by the origin to how far the solvent traveled. So you're taking a smaller number divided by a bigger number. You're not going to have something greater than 1. They're going to be less than 1. And typically you report them as decimals with no units. All right? So, with that definition of an RF value, if we want to decrease RF values, and it's R, capital R subscript F, what will we do to the polarity of the solvent if we want to decrease the RF value? decrease the polarity. So say we had our 1-to-1 ethyl acetate. Would we want more 1-to-1 hexane ethyl acetate? Would we want more hexane or would we want more ethyl acetate? We'd want more hexane, right, to decrease the polarity because the hexane is less polar than the ethyl acetate. And usually with TLC solvents, and then when you get into column chromatography, you usually have something that's relatively non-polar mixed with something that's more polar. So that's why we have hexane with ethyl acetate, something relatively non-polar with something more polar. If we want to increase the RF values, what would we do? Then we're going to increase the polarity. All right. So now let's look at a couple more examples. So here we have a TLC plate. And we're spotting right on that line, and you want to be careful. You can mark where you've spotted with pencil, but just make sure you don't etch the silica. If you do anything to damage the silica on the TLC plate, then you will interrupt how it travels up the TLC plate, and so the chromatography won't work the way it's supposed to. You need a nice sheet of silica for this spot to travel up, or you won't get repeatable results. Okay? So we've got our spot on our TLC plate here, and say we've got compound A developed here. Here is where our solvent is. What do you think we should do to improve the way that compound develops on the TLC plate? Then we're going to increase the polarity, right? If we want it to go up, we would increase the polarity of the eluent. We're not changing the polarity of the spot, it's of the eluent. And we're not changing the polarity of the silica. The silica is always going to be more polar than your eluent. So we're not going to flip this on its head, okay? It's always going to go this direction. So if we want to increase our RF value and how far it travels up the TLC plate, then we increase the polarity of the eluent. Okay, what do you think about this one? Probably would want to decrease the polarity, right? We're getting too high up there, close to the solvent front. Okay. Now I talked about not moving your jar around because you want to be able to move. So this is the distance from the origin to the solvent. So this is our bottom number. This would be the distance from the origin to our spot. It gets complicated if your spots didn't travel nice and vertically up your plate, because then it's hard to measure things and figure out what has happened, all right? So if you move your jar around while it's developing, say we spotted here, and then when we go to develop it and look at it, we've got like spots going off to the side there. It's because things got jostled around, and then it traveled up the side of the plate instead of just traveling straight up, okay? So you want things to travel nice and straight up your plate, not side to side, because it makes things a lot more complicated for comparison, okay? Now as far as your experiment this week, there's multiple places where you're going to want to spot a TLC plate so you can see what is going on with the reaction. And I talked about this reaction goes really quickly. So probably as soon as you spot it, it will be already taking place, all right? And we have we have standards too to compare. So we've got our reactant standard, which is our dienophile and phenolmethylamine, and then we have product standards in the lab that you're going to spot here. Okay, so we've got our final product. You want to be spotting the reactant standard and the product standard on each of your TLC plates. In between, you don't want things too on top of each other. You want to space out your spots and not too close to the edges of the TLC plate because they'll run off the side. But you're going to want to spot your reaction at time 0. And so that time 0 is right when you go, after you've added the cyclopentadiene to your reaction mixture, right when you go back to your HUD, you want to spot the reaction mixture. And you probably will already see the reaction starting to go. Okay? Then you want to spot it at 10 minutes, at the end of reflux. Okay? And you may be able to get that in one TLC plate, or it may take multiple TLC plates. Then we'll have our reactant standard, our product standard, and at the very least, you also want to have where you spot your pure product. Okay? So at the very least, you want time 0, time after 10 minutes, and then when you've purified and recrystallized your product, you want to spot that on a TLC plate and run it with the standards. Okay? So here you may see things, you know, here's, for example, the reactant standard. You might see something like this. Here's our product standard after time 0. Hopefully it's more times, something like that. Ideally, with the pure product, then you want to get to where you don't have any starting material in there. All right, so that's what you want to see when you get to the end. For the pure product, you have to spot liquids. So we have dilute liquids of the reactant standards. You have to spot a dilute liquid on the TLC plate. So you can't spot a neat liquid. It has to be something that's dilute, and your product is a solid. So in your lab manual, it tells you how to dissolve it into ethyl acetate to be able to do this TLC plate. All right? Okay, so now with experiment 12, we've got something a little bit different than we had with the rest of the experiments. It's kind of like our experiment 6. We're going to have a report form that you hand in, okay? So you're going to fill out this top information. You'll give your melting point range, your yield, percent yield, draw the structure of your product. What does it look like? So don't forget this part, the physical description. And this is 12.5 and 12.6 of your lab manual. Then for each of the TLC plates that you develop, you want to draw on this sheet what the TLC plate looked like, okay? And the description of A is what is that spot. So is it the reactant standard? Is it the reaction at time 0? What does A represent as far as your TLC plate? So give the description and then give the RF values of all the spots that you see in there, okay? So you'll do that for however many plates you develop, 2 or 3 plates. Probably not more than 3 plates. Another thing with RF values, they're not like melting points or boiling points. So RF values do not decrease because of impurities, all right? So if a spot is pure, if a lane for a TLC plate, if you see something that is pure, 1 spot means that it is pure, okay? 1 spot is pure. If your RF values are a little bit decreased from what they should be, it's not because of impurities. Something else happened. So if you see 1 spot, but it's a little bit smaller RF value than it should have been, it's not like a melting point where you can say, well, it was a little depressed because of impurities. That's not how TLC works, okay? 1 spot shows purity, all right? The other thing is RF values are characteristic for a certain set of conditions. So in our case, 1-to-1 hexane ethyl acetate. For a certain set of conditions, using that same eluate, you should be coming up with the same RF values for the same compound. So your reactant standard should come up with the same RF value. Your product standard should come up with the same RF value. And then the spots you see as the reaction progresses, should come up with the same RS values going towards products or looking at your starting material. The second page of your report form has, you're going to attach your IR spectrum. You don't need to attach the known ones, standard ones that are going to be on Moodle, but make sure that you fill out all of this table. And what you should compare it to is the known, what the product should look like, but also in this space, describe how it is different from the other spectra, the starting materials. So you should see similarities, but you should also see differences from the starting materials going to the product. And then you will write a one-page conclusion, okay? Hang on just a second for questions. Here, for your pre-lab and your physical data table is information about your starting materials and then your products, so that you have the melting point and molecular formula and weight of your final product, because it's a unique compound. It's not something that you can just buy from Aldrich. So this information you will need for your pre-lab. So I'll leave that up there for you. And then I saw hands with questions. Yes? You'll just be collecting the IR spectrum of your product, of your final product. Those will be on Moodle. Yep. And then the other thing with the report form, those will be due the week after Thanksgiving. Okay, so next week experiment 8 and 11 is due. The following week after, when you come back to from Thanksgiving, you'll be handing in your experiment 12 report form and conclusions. So we'll talk about those in lab this week and follow instructors' instructions on those guys, okay? So next time I see you, those will be due that week, and then we'll also talk about the final exam one.